Hello students, welcome back. Now we are going to design a counter which can count 4 different values but using a finite state machine. So in this video we are going to talk about that how can we count using a finite state machine. We are going to design a counter using finite state machine and implement it using Verilog. So let us get started. So first of all, we have to talk about the problem statement. We have to count up from 0 to 3 and keep repeating this process. In binary, if we say we are going to count from 0 0 to 1 1. No separate input will be required. We will always keep counting up. So what we can do, we can define 4 states. Those will be S0, S1, S2, S3 or any names that you find relevant. And then we will describe the counter as a Moore's machine. So let us have a look at the state table. What are we describing here? We have our present state which is S of t and there are 4 possible values S0, S1, S2, S3. The next state calculation is dependent on input. So whenever the input is 0, present state and next state they are same. And whenever the input is 1, we are going up. S0 will go to S1, S1 is going to S2, S2 is going to S3 and S3 is rolling back to S0. The output which is Z of t is independent of input. Whatever is the value of present state, based on that the output is fixed. Now the important part is how do we implement this in Verilog. We are going to use case statements. If I have n number of states, I will use those many cases. One case for each state. In each case, then we will define that how to calculate the next state and the output assignments. So now let us go to Vivado and implement this finite state machine based counter in Verilog. So we have our module which is FSM underscore counter. There is one input which is clock, there is one input which is reset, one input is D in and the output is Z. Clock, D in and reset. These are all single bit wire inputs. Output, because we are going to count from 0 to 3, so we need 2 bits. So it is a register 1 down to 0. We are going to declare 4 states. So I declare one register which is of size 2 bits and the name is state. Now here is a new concept. We are defining parameters. I say S0 is basically 0 0, S1 is 0 1, S2 is 1 0 and S3 is 1 1. This is an optional thing which will make the coding in Verilog for FSM more clear. So how do we start? We say always at the rate positive edge of the clock, begin and end. Only this much I am writing first. If reset is equal to 1, my state goes to S0. And what is S0? 0 0. Else the state remains same. So if I make my reset signal as 1, the counting will come to 0. Next, I again start one always block which is again triggered by positive edge of the clock and we say case state. Based on the value of state, we are having 4 cases. One case is S0, one is S1, one is S2, one is S3. In S0 we are writing if data input is 1 with some delay, state becomes S1. Otherwise state remains state. Okay, that means if input is 1, next state is S1. Otherwise, if input is 0, then state remains the same. Next case, that means my present state is S1 and if input is 1, the next state will be S2. Otherwise, it remains same. You could have very specifically mentioned S1 also. Okay. Although whenever we are coming in S1, it is clear that state value is S1, but it is never a harmful thing to mention the specific value. Okay. So for 1 it will go to S1, for 0 it will remain 0. In S1, if input is 1, we go to S2, otherwise we remain in S1. Similarly, S2 will go to S3 or it can remain in S2. And S3, if input is 1, we will go to S0, otherwise we will stay in S3. We are ending our case here, and this is the end of always block. Then we define one more always block where we say always at the rate positive edge of the clock, assign z is equal to state. So whatever is your present state value, that is my output. So this is the simple code that we have. I am going to revise it again. First of all, we have reset condition. If reset is 1, we come back to 0. Otherwise, we remain in the present state. Then we talk about 4 cases: S0, S1, S2, S3, and then we finally allocate the output. Now let us have a look at the simulation. Initially, reset is undefined, din is undefined, so everything is undefined here. We start with reset equal to 1. So when reset is equal to 1, clock has just started. In that case, the value of z, that means my output, will remain 0. After some time, I am making the value of d in as 1. And when I make my value of reset equal to 0, then you can see from 0 I started counting up 0, 1, 2, 3, 0, 1, 2, 3, and so on. We can make reset equal to 1 and stop it again at any value. So students, now we know about the implementation of finite state machine based system in Verilog. We are going to discuss another interesting system in the next video, and that is pattern detector. Keep learning. Thank you.